Okay, good afternoon, everybody. It's my pleasure to welcome today's speaker, Terry Rudolph from Imperial College. Okay, Terry has interesting connections with interesting people and interesting places. First of all, you've all heard of Schrodinger's cat. Well, Terry is actually Schrodinger's grandson. Okay, he did his undergraduate work in Australia, and then he came to Toronto to do his PhD work, which he did at York University with Helen Friedhoff, who I'm pretty sure was the first woman professor of physics in Canada. Okay. Actually, Helen and I had the same PhD supervisor when we were doing our PhD work. So that means that sort of scientifically, Helen and I were sister and brother. So although Terry may be, Terry is Schrodinger's grandson, he's also my scientific nephew. I knew it started with N. I didn't remember which one. Anyway, when Terry was finishing up his PhD, before I met him, I got a phone call from Helen, who actually, she did her PhD about a decade before I did. Got a phone call from her when I was acting as associate chair. And she said, I've got this really great graduate student, and he's going to go on and do great research, but he's sort of young. And I think it would be good for him to do some teaching for a few years. And well, you know, your older sister tells you to do something, so you do it, okay? So in the end, indeed, he came to the department. He had a spectacular 2 years doing teaching here, which was very, very successful, okay? Then he went on to Vienna to do a postdoc on the Bell Labs, and then to Imperial College, where he is now, which was actually the same place where his supervisor, Helen, did her postdoctoral work, okay? So, he's known for having done a number of very interesting things in quantum mechanics and quantum optics. Let me just mention three. One is the PBR, okay, theorem or argument that has to do with ontic states in quantum mechanics. The R is Rudolph, that's him, okay. He's also done some very interesting work on trying to explain quantum information to people in high school and just starting out in universities. Okay, and finally, he's working on he's doing work on fusion-based quantum computing strategies, which led to him being a co-founder of PsiQuantum, and he's going to be talking about some of that work today. So please join me in welcoming Terry.
Thank you, Uncle John. I should say before I get going, I have to leave pretty promptly at the end of this. And if you have burning questions, just ask them during the talk. That's fine. I might not be able to stay around for much at the end. Yeah, so I'm going to tell you, about quantum computing with light. I was a comfortably ivory-towered academic at Imperial College until about 2015. And then ended up in 2016 being a co-founder of PsiQuantum. And that's taken me to Silicon Valley into the crazy world of having a company. In 2017, the company looked like this. Several of my former PhD students, my co-founders were Jeremy O'Brien, Mark Thompson, Pete Shadbolt, and we were sitting there with what seemed like a large amount of money and saying, okay, now how are we actually going to build this quantum computer? And if you ever watch the show Silicon Valley, what you learn is that the less you say about what you're actually going to do, the more money people will give you. And so, a few years later, we now find ourselves in this kind of crazy situation of being 500 plus people. We've raised eye-watering amounts of money, and we're building a whole bunch of stuff. And I will have succeeded in this talk if you, by the end of the talk, have some sense of where the hell did all that money go, because I'm pretty sure that's the main question you should have. By the end of the talk, I'm hoping you look at what we're doing and go, yeah, that looks pretty expensive. And not the sort of thing that you could do in academia. Okay, so here's why people give us money and give other quantum computing efforts money. It's that quantum computing is a kind of multidisciplinary revolutionary tool that you can basically speak to anyone in whatever they do that's technical and say, oh yeah, a quantum computer, it's going to help you with, new fuels or photovoltaics or new batteries or, listening to people or making drugs. Everyone is affected by things that quantum computers will one day be able to impact. And I should emphasize that, the promise of the quantum computing is not to, just compute the same things, but a little bit faster or with a little bit less energy. It's really to start computing things that even if we turn all the silicon in the Earth's crust into a classical computer, we know we can't solve those problems. So the reason why there's this excitement and why we will keep going on building quantum computers, until they come, is really just that there is no other way of solving some of those problems. Now, the thing that this little narrative leaves out is captured in this little schematic here, which is it takes a very large quantum computer, very large, in order to solve, or as far as we know, in order to solve the problems that we think of as genuinely useful. So this plot here is just the date, starting in 2010 to 2030. And this measure here is basically the number of qubits times the number of gates you need in order to solve a problem. And so what you see is that as as time is going on, we're getting better and better at solving problems. So this is like the Fermi-Hubbard model. These are some quantum chemistry problems. There's even some finance problems in there. And this derivative you can interpret as like the intelligence of the people that are working on the problem. So, but the scary thing is that you look at this and we're looking at very big numbers here. And that's even if we have a perfect quantum computer. What we would say is that the number of logical qubits times the number of logical gates has to be very high. And in actual fact, we know we're going to build a quantum computer from imperfect things. And what that means is that we have to do error correction. And the whole theory of quantum error correction and fault tolerance, which is developing very rapidly, still says that we're going to need something like a factor of 10,000 extra on these numbers just to deal with the fact that we have bad components and bad devices. So what that means is that when you look at a picture like this, there's sort of two ways of interpreting this. This is the Google quantum computer. I think it's the most impressive quantum computer on the planet at the moment. And this dilution refrigerator here sitting in the bottom of it, most of this is not the computer. Sitting in the bottom is a tiny little chip with about 100 qubits on it. And this tiny little quantum computer can do something that no classical supercomputer can do. And the classical supercomputers are these massive things. They're like data center sized machines with coolant pumped around them, and they're full of GPUs. And this tiny little 100 qubit thing can do a calculation that they cannot do. The problem is that calculation is basically simulation of noise. It's not a useful calculation, but it shows there is this massive gap between quantum and classical computing. And when we founded PsiQuantum, we charged around Silicon Valley saying, look, it's pointless to make these small quantum computers because it's going to take millions of qubits to do it. And really no one listened to us for about 2 years. And we finally got some seed investment and so on. And, it's been gratifying that since then, everyone has realized, yeah, you're going to need millions of actual physical qubits in order to make enough logical qubits and enough logical gates that you can solve useful problems. If you don't believe me, and why should you? I'm just a physicist. Believe these people who are very wise and run very big companies. They'll all tell you the same thing. And they all have their own quantum computing efforts. And they'll all say, that to get there, we need 1 million qubits. And so everyone, not just us now, looks at what they're doing and says, how am I going to scale this thing to a large quantum computer? And really, there's 4 things that affect scaling. You start with your qubits, but everyone's got nice qubits. They're easy enough to make. Some sort of way of making some kind of small-scale quantum states. There's 4 things that really dictate how big a quantum computer you can make. And those are, if you're building any kind of machine from a billion or a few trillion components, the only way humans know how to build such machines is through manufacturing and semiconductor manufacturing processes. So you have to have some, most of your machine has to be manufacturable. All qubits right now need some cooling / laser / whatever power. Control electronics, you saw that cryostat, that Google cryostat, like almost all of that stuff is just like lots of wires and controls just to try and control this tiny chip. So these things can be pretty hard. And then depending on your approach, but the vast majority of approaches, there's no possible way they're going to fit millions of qubits into a single cryostat. And so they need some way of connecting them up and modularizing the architecture in such a way that they can actually keep scaling the machine by building more and more copies of the same thing. And so when we found the PsiQuantum and we were talking about fault tolerance, the reason we were doing it, it's not like I did not ever want to be a founder of a quantum computing company. I was perfectly happy doing what I was doing. But it was because we realized that this piece here was now within sight for photonics. And photonics, we encode our quantum information in photons. And silicon photonics had sort of gotten to the point where we were like, yeah, we can stare down being able to manufacture these very large number of component machines using standard semiconductor processes. And so that's what kind of drew us in and said, okay, we really got to have a go at doing that. Now, you can see that sort of reflected in our team. So in the 400 and something odd technical people in the company, there's they break up into the architects, who are the people that have to lay out like the theoretical design. What are the quantum states we're making? How are we connecting them? What are we doing? And then the hardware engineers. The vast majority of the hardware people are from the semiconductor background. So in all of these people here, there's only sort of on the order of 40 or 50 physicists, people with physics PhDs, and then there's a heck of a lot of people that don't know any quantum mechanics at all, but they do know how to build stuff very well. And so in the rest of the talk, what I'm going to do is I'll start off by telling you what the architecture team do, which is what I'm basically in charge of at the company, which is to just sort of abstractly say, how are we going to make a big quantum state and do a quantum computer? And then I'll go on to tell you what the hardware engineers do. And they, the vast majority of them don't actually sit in a lab. They sit behind a computer, they design something on CAD, they send it to get made. Of course, a small number of them sit in a lab testing things, but the majority of them are experts in essentially in manufacturing chips. Although as the company's gotten bigger, we now have a whole bunch of engineers that come from things like the oil and gas industry, because we've got to build large cryo plants and cryostats and so on. So it's sort of interesting to watch the transition. Okay, so let me talk a little bit about the architecture of what we do. And we don't just sit around thinking. We have to actually also, do simulations and do some mathematics and convince ourselves that this thing is going to work. Our qubit consists of a photon that is confined into a waveguide. So you should just think of this as I have a piece of silicon and someone digs a ditch in it. And what that ditch does is it traps a photon in it. And you can dig the ditches in such a way that you can bring them close together. They're not exactly touching here. And if you've done undergrad quantum mechanics, you'll know that, okay, when I have a potential barrier, a weak potential barrier like this, I can get some tunneling. And so what can happen is that a photon can come along here, and we'll call this our qubit state 0. And if I make this what we call coupler the right length, it'll have kind of 50% amplitude for tunneling over here and 50% for tunneling over there. I can apply some phase shifters. And this here is just the silicon chip version of a beam splitter. And this is just a silicon chip Mach Zehnder interferometer, something you can often make in undergraduate labs, but it's now done on a tiny scale. And if we can do it once, we can do it 1 million or 1 billion times. So the single qubits of what we make are fine. That's great. I hate to break this to you, but you were lied to when you were told that you could make lightsabers. Light doesn't interact with light. And this is the real problem for photonic quantum computing is that we can't get the photons to interact with each other. And so building one of the biggest challenges is, well, how do we do multi-qubit things? A quantum computer needs multiple qubits, making some kind of exotic quantum states. And although it is a big challenge, it is also one of the opportunities of photons. They don't see noise nearly as badly as many other approaches. And so when I try to explain to my mum, and this explanation, hopefully works for you, maybe if you ever try and explain it to your family, like, what is a photonic quantum computer? I say, like, when you're sitting in the living room at night and you have a lamp on and you look in the window and you see this partial reflection of yourself sitting there, you basically have the elements of a photonic quantum computer. You have a source of the light. Photons go from that source, they hit the window. And then when they hit the window, they go into that superposition of either being transmitted through the window or coming back. And then your eye acts as the detector for the photon. So you have almost all the elements we need. The only thing you're missing is a switch. And a switch is as simple as a mirror where based on you've made some detections, you can reroute some other light. But photonic quantum computing is sort of easy in some senses because of this. The quantum mechanics of what we do is very trivial. But we do need this way of how do we get something, how do we get around the fact that the photons are not interacting with each other? And although photons don't interact, they do interfere. And this is the key effect. I'm sure if you've if you've worked in a photonics lab, you hear about this thing. It's called the Honger-Mandel effect. And it's a very basic feature of bosons, essentially, that you can get if you put, like in this case, say two photons that are identical in everything except kind of their spatial mode, like which waveguide they're trapped in. If you put them through one of these interferometers, you can get a cancellation in the Feynman paths, essentially, for these things, such that that they always bunch together. And if they were not identical, they would not bunch together. But if they are identical, they really will always come out of the same port. The final state will be a superposition of these. But it's this thing that we use. And it looks like an interaction. It looks like that one photon must have known that the other one was there. But if you go and work it out, it's not an interaction in the physics sense. It's like it's a free field Hamiltonian. If you're a quantum field theorist, there's no interaction term in the Hamiltonian, but this is just a property of mode transformations in free fields. And so it's this effect that we need, but to make it work, and this will be relevant later, we need the photons to be identical in all of their properties except which waveguide they're in. Okay, so the sort of summary of our architectural approach is that we want to do fault-tolerant quantum computing. There's really two ways that people have looked at, two sort of extremes. One based on what we call circuit-based quantum computing. This is where you have static arrays of atoms or superconducting qubits and do sort of nearest neighbor type gates between them. So you do entangling gates and entangling measurements on them. There's a completely different approach. I'm not sure anyone's taking it sort of seriously in terms of building large machines, but it's theoretically one of the most interesting things I've encountered in my career, which is that you can actually start with a large amount of entanglement. If you have some way of generating large entangled states, you can get by with just doing single qubit measurements, and they can even be destructive. You don't need the qubits there anymore. And when we started the company, we thought we might tackle something like this. In the end, we've come to something which I think of as a bit more like a Goldilocks architecture in between, which is based on the following. Rather than doing single qubit measurements, which always destroy entanglement, we on a large state, we take small entangled states, and then we're going to do 2 qubit measurements between them. And those measurements are the things we call fusions, and they're basically just a probabilistic Bell state type measurement. But the key thing is the following. For us, this represents, say, 6 entangled photons. It doesn't really matter how many, your approach to fault tolerance, it might dictate that you need a 10 photon entangled state or 20, but whatever it is, it's some fixed number. It can be as low as 2 or 3. And the measurements that you do create entanglement, but they also destroy the photons. And why that's important is that, well, it's hard to do non-destructive measurements on the photons, but why it's important for us with the photons is that this means that from birth to death, any photon that we produce only goes through a fixed number of optical elements, no matter how big we make the quantum computer. So our quantum computer is going to scale by making more entangled states, not by making life harder for any photon in any particular entangled state. And so this is very important because in optics, loss is the main error mechanism. And if you have a certain percentage probability of losing a photon at every step, that will accumulate exponentially badly. So you really have to have a fixed optical depth architecture. So yeah, this is very abstract. Let me show it to you as a kind of even slightly more animated version. You can imagine this is a whole bunch of stuff, photonics and lasers and switches and stuff that make these 6 rings of entangled states. And you can see in this little animation that a ring of 6 is made, and then those little yellow flashes are meant to represent doing this fusion measurement. And the fusion measurement is very easy to do. It's a couple of beam splitters and detectors. But what's a little bit hard to see with well, at least from here, but a measurement produces classical bits. And so what I want you to think of is that this computer, if you just think of it as a block of space-time, it's like a layer of kind of quantum-y stuff going on, and these measurements, and a whole bunch of like classical bits that fill up this volume of space-time. And the claim is that if I go around and I just sort of look at the outcomes over here, I can detect if there's been errors in the system, and I can also detect what gates I'm doing, and choose what logical gates I'm doing. And the computation is actually just choices of phase shifters that we do just before the fusion measurements. And I know that this is a strange architecture, but if you're in quantum computing in a more standard architecture, you're probably used to something that looks a bit like this, which is where you have an array of, say, superconducting qubits, and you do pairwise, you take qubits and do pairwise C0 gates. So here's a quantum circuit for doing this thing. And then you make some non-destructive measurements on your qubits. But at the end of the day, this thing here just produces some classical bits that we call the parity checks. And those classical bits also embed in time, because I don't destroy these physical qubits. They just sort of, from one time step to the next, create more of these classical bits. And if you go and just look very abstractly at this block of space-time and the classical bits in it, you see a whole bunch of correlations in them that are like Bell correlations and these sort of parity check correlations that in this quantum computer and this quantum computer, you can kind of make them the same. So any approach to fault tolerance in the one way of doing quantum error correction fault tolerance can be implemented in the other. So at the end of the day, all quantum computers at a high level are going to sort of, I think, are going to be the same. And microscopically, the physics might be very different, but we're all kind of doing the same thing. Okay, so now the architecture team's job is to tell the engineers, like, okay, we need to make these 6 rings, and here's how, here's a bunch of interferometers to do it, and then they've got to come out at this particular clock cycle rate, and then you've got to route the photons here and there and do these measurements and so on. So we give them a design, we send them a design, it looks nice and beautiful, and what they send us back is stuff that looks like this, right? And so our job is to iterate on all the different things that are hard for the engineers and go, okay, well, if you can make this thing a little bit better, then that thing can be a bit worse. So there's all these trade-offs in any approach to building a quantum computer. And it's understanding that parameter space of trade-offs, which is what the theoretical physicists at PsiQuantum do. There's sort of many parameters, they're sort of constraints or error rates, or like, what's the variance in a phase shifter, and how distinguishable are the photons, and how close to a 50-50 beam splitter do I make this thing, and so on and so on and so on. And we have, I don't know, order of 40 or 50 or something of these parameters that we then have to make models for and work out what are the imperfect quantum states that we're making, and can we still do a fault-tolerant quantum computation even with these imperfect states, and what error correcting code should we need to do, and so on. And because we don't have a quantum computer, we have to simulate all this stuff on classical computers. So a large number of people are either numerical physicists or software engineers that work with them and help them write better code. And we have this whole kind of simulation stack that really is like 5 completely different suites of software. And then there's actually one that I'm not showing here, which is what the applications and algorithm team use for compiling quantum circuits. But we really have the ability now to say, okay, look, here's a waveguide, and it's got like, you know, this ditch that the photon's meant to be running down, but the ditch has some little wiggles and variations, and it's not perfectly smooth. And to the engineers, they call this an LER. It's a line edge roughness, and it's a really critical parameter to them. And then we go through the simulation, we go through here, you know, we make some sort of abstract linear optical circuits, and then at some point we can't do this anymore. We have to start turning our states into what are called stabilizer states, which are things that we can simulate. And then then these are the mathematical structures that are that determine the fault tolerance. Because we use photons, we can use much more exotic error correcting codes than most people, because we're not restricted to three dimensions of space in the same way. Blah 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 blah. And we get out here, and then the people who run these simulations, they get out what they call an LER, which is a logical error rate. And the logical error rate, you know, you want it to go down as you have more things. But the reason I bring that example up is, like, to be able to go from an LER to an LER, I think we were definitely the first company that really did this. It took many years and many tens of people to be able to do that. And it also emphasizes that you've got to make sure you're communicating between engineers and physicists very carefully, because there's so many acronyms that get used in the company, and make sure everyone knows what they mean. Okay, so now I'm going to show you what you know, I think is you know, synopsis of the most important hardware progress that we've made in trying to actually implement that abstract and kind of theoretical design. I am not a hardware person, as you can tell. I am not an engineer. You know, I'm continually presenting this work as if it's, you know, stuff I understand deeply, and I don't. And so if you really want to get me confused, well, just kind of ask anything past what I'm showing you on the slides, and I'll probably be confused. But this slide captures kind of how I think of our machine. Okay, like, what is it that we're building, like the actual stuff going into this machine? And I think what's remarkable about it is that the stuff we're building, we care about things on the scale of from an angstrom up to hundreds of meters. Okay, the photonic components that we make, there's really only 5 photonic components in the machine. There's a switch, like the mirror on a stick to route the line. There's the detector, like your eye, to detect it. There's the source. You know, a lamp, unfortunately, is not a good enough source for what we need to do, so we have to have a way of making photons. The interferometer, that's the thing, that's the beam splitters and the couplers and the waveguides. So we have to make interferometers. And then the last one, which is sort of special to silicon photonics, I guess, is that we also need a way of taking a photon off a silicon chip and then putting it into an optical fiber, and then taking it all the way over to a different silicon chip. And that thing's called an edge coupler. And at the component level, that's the thing that, you know, most keeps me awake at night. It's a very silly, simple thing. It's basically a classical light problem. It's got nothing to do with quantum mechanics, but the kind of shape of the photons as you send them down the waveguide, you know, is quite different to the shape the photons want to be in an optical fiber. And one of the miracles of optical fiber is that it really only accepts photons of a particular shape. And so you spend a lot of your life just trying to convince the photons along the waveguide to, like, kind of change the way they are and then jump into an optical fiber. Anyway, so yeah, that's what an edge coupler is. So these things, we care about the manufacturing kind of at an angstrom level. You know, we're controlling parameters to an angstrom scale. We then have wafers, which I'll show you more about that, but they're on this, you know, they're a bit size of a piece of pizza. It's like a 30-centimeter wafer. Then we package these things, these chips, into these sub-assemblies. So we start with packages of a couple of chips, and then we make sub-assemblies of sort of tens of chips. Then those things go into cryogenic cabinets. Those cabinets are a little bit higher than me. And then the final machine is hundreds of these things. Along the top here, what you're seeing are artist renderings of all that stuff. On the bottom, you're seeing stuff, and I'll show you a lot more of it, that is actually being built. As you can see, we are not at this point here, but everything else at every other scale is stuff that we are actually building. Okay, So I'm going to show you a little video, though, that we show new employees when they come into the company, even if they're not really engineers and into that kind of thing, just to give them a sense of the scale of the machine that we're building. So this little video just is, you know, it is sort of an artist rendition in some sense of the machine, but it's based on accurate scale models. Yeah, let me see if does this thing play. So we start off with wafers. They themselves are made up from, you know, many materials stacked. The wafers that come to us broken up into these chips. The chips, any individual chip will have a bunch of components, things like single photon sources and filters and detectors, depending on the chip. Those get stuck onto those copper back planes, down which liquid helium cools the back of the copper. We need liquid helium because our detectors need to be cold, and I'll explain how in a second. But then one cryostat is you know, sort of order of hundreds to thousands of those chips. And then a whole bunch of other stuff, which is lasers. We need lasers for the sources, control electronics, things to read off the signals, things to do, processing, and so on. All of that's one cryostat. And then the whole machine is, you know, this sort of scale of stuff put together. So it's really like data center size thing with, you know, I don't know, order of 100 odd meters or 200 meters from one end to the other. So if nothing else, I said, you know, you should be able to go away and say, you know, where the hell are these guys spending all their money? And it sounds like we're building big stuff. Like, you know, you can't build this in the basement over here. It's just a completely different scale of game that we have to play. Okay, let me talk a bit about the actual manufacturing, because I think this is this is really the key to being able to build, you know, billion component machines. We have to do a whole bunch of semiconductor manufacturing. This is Global Foundries. It's their Malta Fab 8. It's their kind of most advanced fab. This is upstate New York, not far away. Toronto, somewhere on the other side of that lake, I guess. And this is the inside of a place. Like if you say, you know, where do the chips in your laptops and cell phones come from? They're all made either here or in an almost identical foundry somewhere else in the world. They're highly clean environments, lots of robots picking things up, moving them around, you know, taking layers of material, stacking them together, etching them down, all this kind of stuff. And so it took us a few years to convince Global Foundries to basically let us in the door, you know, because they're not in the game of like doing silly science experiments, and they don't want to mess things up. But we did manage to get in the door, and then we sort of got to the point where now they even have a team of people dedicated to us, and we have a whole bunch of people there at Global Foundries full time. We own a bunch of tools there that they've put in the floor just for our own use. And when you look at one of our wafers, now the annoying thing about coming to Canada, like I normally travel with a wafer, I could show you, but I was like, I'm not going to cross these borders a couple of times carrying a whole bunch of silicon chips on a wafer or something and find myself like running afoul of you know, customs people on either side of but I think one side's more problematic than the other. So, but yeah, so unfortunately I couldn't bring you one. I can only show you the pictures, but it's kind of cool when you get to see them. But if in making one of these wafers of chips, we made about 4,000 of them. There's about 900 process steps. There's about 40 different mask layers in terms of making any given wafer. We own 11 dedicated mainframes. So a mainframe in a silicon foundry is kind of a robot surrounded by these sort of chambers. You know, so you want to keep stuff super clean and sort of not have to put it in the air until you finish doing stuff. So we have about 11 of these kind of what they call mainframes. And then we have a whole bunch of testers and wafer testers and chambers and so on. But my favorite machine that we have at Global Foundries is this thing here. So this thing in the background, which cost us some eye-watering amount of money, is essentially an expensive dishwasher. So, and these are the people who run the dishwasher. They're not very good looking, so we make them cover on. But the thing with this dishwasher is purely just to clean. So there's one material, the material we use for the switch that we make ourselves. We have to send it to them, and then it has to be ultra clean and pure and polished and so on. And this machine just does that. You know, it's just some kind of huge amount of effort just goes in these foundries into just making sure everything is kind of ultra clean, pure, precise, and so on. And then the wafers, if I was able to bring you one, come out looking like this, and then that's the thing that gets broken up into the chips, okay? Now, the thing is, on any of these chips, there will be thousands of photonic components, potentially tens of thousands, it depends a little bit on which part of the machine the chips are for. What that means is that, and now, you know, we're iterating on designs. We are trying to build better and better components to make a better and better machine. What that means is that we can't, we have to test these things in a very automated way. You cannot test wafers like that with machines like this, because these machines, they like need to eat food, and you know, they go home and they like sit there and bump things on a table and so on. You cannot do this. So what we do is we hire robots. They also smell better, these robots, and they essentially take the wafer into a large stack of what kind of looks like an old CD changer that you would have in the back of your car if you're all too young for that. Not all of you are too young for that, but most of you are too young for that. But it just takes these wafers in, and then it reads where it is on one of these chips, and it goes along and either injects light or current, depending on what type of thing it is, reads out where it is, runs the tests. The tests are all sort of pre-specified by the engineers, and then uploads that, and then that feeds onto the next design of whatever the next component is. And then, of course, there's all these different performance characteristics of the different components. I'm just showing 6 here because I dug it out of someone else's slide deck. But you know, as I said, there's sort of, you know, 50, 100 of these or whatever it is that really matter to us. And the architects tell the engineers, like, oh, this is what you've got to reach. So this here is for, say, the edge couplers. You know, we want you to be at 30 millidB, this is. And then, you know, the robots give us this information about, like, oh, as time goes on, we're getting better and better. And sometimes the engineers get better than the threshold, sometimes they're worse. And then the architects go back and say, okay, well, I can deal with this, but, you know, you let me trade that off and so on. There's a lot of design stuff goes on. What's important, though, is that this is the performance. We need the performance of this thing, not in a hero single-shot experiment that you send to nature and then go off on your summer holiday. We need it on average over millions of components, over many different wafers and devices and so on. And so, you know, single points like this are not actually that informative to us. And we need that performance to be not just when they're in an individual chip on their own, but when they're built into a subassembly for the machine. You know, sometimes you get degradation of performance when you start putting this stuff together. And so actually what we care about more in terms of iterating design are these things, which are just sort of wafer maps that tell us, okay, as I vary over a wafer, making the same chip over and over and over and over again, how is the performance of the components in that thing? And we test tens of millions of devices a month, and we get out wafer maps like this for everything. So this is the wafer map for like a crossing on this chip. Like if I have a photon going this way and a photon going that way, the two ditches that you dig, you're a bit worried that the photon might hit the edge of another ditch and go into somewhere else. So we try, and this number ideally would be 1.000, but it's not quite. And then we need to know, how does that vary? And the great thing about photonics is that we get this information without cooling the chips down because of this miracle that John will explain to you, that single photons and classical light essentially act the same way in terms of how they move around. And so we get all this information, and we tell the engineers, okay, now you can change this design. Well, they run their own simulation stacks to do this. And then we keep iterating on these designs to get these numbers better and better. This is the performance of the 50-50 beam splitters. And so this is the kind of large scale data analysis, feedback, and so on that we did not invent. This is what the silicon industry does. Those testers that I showed you were not robots that we built. They're the same testers you would find at Intel or at TSMC or so on. And we get out all this information. And what I think, the point of this slide is, here's another wafer map. I can't even remember what is this for. Yeah, this is just a sort of loss in a waveguide type map. But this progression down here is just, the engineers started off at GlobalFoundries. The first runs were just terrible. And then as time went on, they got better and better and better. And you can see them converging down to these incredibly low numbers here. These are far and away the lowest loss waveguides on the planet, as far as I know. And really, this is just this back and forth on automated design. Here's another one that I throw in just to annoy one of my co-founders. In 2012, when he was a PhD student in an optics lab, he kind of made this psi symbol in the Bloch sphere of stuff that he could make, 98% fidelity, and he just kind of published it in a paper that ended up in Nature. That wasn't the point of the paper, obviously, but anyway. He did publish this in a Nature Photonics thing, and this is what we can do with psi, and this is just completely automated, digital, kind of similar kinds of things. So, okay. So I'm going to give a brief synopsis of, as I said, there's really only these 5 things. So what's stopping us from building a photonic quantum computer is that all those 5 things have to be good enough. Well, then they have to all be assembled and remain good enough, and then assembled into a bigger thing and remain good enough, and so on. So let me give you the sort of brief summary of how the progress on all of those things have gone. Our single photon detectors, the photon comes along, it hits a little piece of superconducting niobium nitride that's sitting on top of the waveguide. It's a well-established technology, creates a hotspot, breaks the superconductor that causes a electrical signal in the wires that the superconductor is attached to. Blah, 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 blah. We should be detecting single photons. In practice, the real challenges for the engineers are not so much this, but the fact that we then tell them, okay, you're going to put a little piece of wire on a waveguide that can detect single photons. Oh, and less than a centimeter away, I'm going to stick a laser that's 1 trillion times brighter or even more to create single photons. And you better just put something there to block it, And this kind of thing is actually, I hadn't appreciated, the kind of stuff that keeps your engineers awake at night more than anything. Because, stray photons from the laser can run around and they've got to go somewhere, and they go around, they bounce around. And if they get absorbed here, then we end up with a spurious signal. It's not the single photon we wanted. It's some other one of these many lasers. And we have heaters, not on the more recent designs, where we used to have heaters that were hot next to these things that needed to be at a couple of Kelvin. So making these chips really is a nightmare. The kind of thing, here's a little animation. I mean, it's quite old now, but it shows you, this is scanning tunneling microscope. It's not just animation. This is an actual device, a detector. And then we put these things are kind of big plates of gold that block the lasers. This is where the laser gets shone into a grading coupler here. And then this stuff that's blocking these photons is just these kind of gold dug down into the chip. And by some miracle, it did actually work. And we do get the suppression down to, it's like more than 120 dB of suppression of this laser line. And that's good enough for what we want. And to give you some sense of how good the suppression is, it's like someone sets off a nuclear bomb at that corner of the room. And by the time the sound gets to me, it's like this. Okay, like that's the level of suppression you need to make one of these things work. It's kind of crazy. Just finishing on detectors. Here's kind of what they more look like when they're in an actual circuit, which is that they have to get read out, and so they're sort of the detector chips and the electronic chips coupled together. And the detectors have to be cryogenic temperatures. They sit on this sort of heat sink. And then this here is just some data showing them counting photons, counting 1, 2, 3, 4, 5, 6, and so on. Actually, we don't need to count more than 3 photons, but it's nice to be able to do it. And so, yeah, that's detectors. So next thing is the sources. I really threw this in for John, because John has done a lot of nonlinear optics. That should warn you away from nonlinear optics. Look at how unhappy he is. And one of the things that John showed actually in many years ago now was that you can make pairs of photons, highly correlated pairs of photons by pumping waveguides in the silicon that are like a ring here. But if you do that, you're not going to get better than about I can't remember the number. Do you remember the number? Or you something like 90% purity. Okay, and so what we need is much higher than 90% purity, and it's captured by this. I'm not going to spend too long explaining this, but what this basically diagram is telling us is something about how correlated or how entangled a photon is when I produce one of these pairs. And actually, we don't want those photons entangled, because the way we make our single photons, it's very wasteful, but it's like we make a pair of photons, and then we detect one of them, and we say, aha, I saw one here. I know that there's one over there. But if you've suffered through, doing undergraduate quantum mechanics, entanglement, blah, 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 you know that if you have an entangled state, then the reduced state of a single system in entangled state is mixed. We don't want a mixed state. So actually what we want is these photons to be kind of correlated, but not adding to the mixture, like not mixed. And John had this theoretical bound that said you can't get better than, I think, 92 or 93% something. We got up to about 90%. But these are useful to build. It's not that we didn't believe you, but we did still build them. But then we started iterating on source designs, and we got up to higher and higher levels of purity. And now we make these kind of array resonators of these things, and we get to insane purities. And when I first started showing this slide, underneath this picture here was a simulation, because we hadn't proven that this could work. And then we got up to the point where we actually were making these things, and we could get this extremely high purity of our heralded single photons. So that was quite gratifying. And what's sort of great to me about it is that these arrays of sources, we can take a single photon that's made on one chip on one wafer, and then take a single photon made from a chip in a different position on a different wafer that's like tens of wafers down the run. So these things are made completely independently. We don't need to apply tuning and filtering and anything. We can just literally do a Hunger-Mandel interference experiment with them, and we get out these kind of high purities and high. Does anyone in your lab do like still doing home stuff? I don't know. Maybe. Well, maybe they'll like this diagram. But all of this stuff. The point is that yeah, you should not try and do a PhD by just doing HOMDIPs. That worked for the people who won the Nobel Prize a few years ago. Doesn't work anymore, because we can just automate the whole thing on a chip. So you got to do something. You got to do like at least 2 Hunger-Mandel effect tips or something if you want to get a PhD these days. All right. The edge coupler, I'm not going to say much about. As I said, it's just the pain of trying to get a photon to come off a wafer and go into a fiber. And what matters is the probability of loss. And where we need to be is around here, 30, 40, 50 milli-dB, that kind of thing. Ideally, we'd be about here. And those numbers are coming down, but I put this in because I want to emphasize that the challenge for photonic quantum computing is as much about silly mechanical things. We've got to glue fibers. Like the challenge of this is we've got to stick this fiber. We've also got to glue it on here, and we need robots to do that. You can't just have someone sit there by hand do that. So you need robots to do that, and it's like mechanically lining up this big circle with this like little waveguide and making sure all of this stuff. So it's very much kind of classical large-scale engineering as much as it's quantum anything at all. Okay. Now, the sort of crowning glory of our hardware effort is the optical switch. Optical switches are super critical for us because we have these probabilistic things going on. So this here imagine there's 4 of our heralded single photon sources. So a pump laser comes in, creates a heralded single photon. We detect it here. And then we need to send that detector signal to some electronic circuit, which then triggers a switch, because we're only creating a photon with a low probability. Okay, we run at sort of between 5 and 10% probability kind of thing for making the single photons here. This means that we want to switch out the photons that we make, and in this sort of simple animation, we want to switch the photon to always come out here. But that means we need a switch over here that, regardless of which of these ports the photon comes in, it can always get switched out there. Now, the problem is electronics are slow, so we have to delay the photon. So we literally put it in. It seems dumb, but that's just the way to do it. You just dig a spiral and let it go in and let it come out, and that gives you enough time for this electronics to decide how to set some phase shifters. And this here is just a fancy Mach-Zehnder interferometer. It's very similar to Mach-Zehnder, the 2-port Mach-Zehnder interferometer, but now it's got 4 ports. And the largest switches we make at the moment are about 64 such ports. Okay, we will soon be taping out ones with 128 ports, and that'll be the largest I think we ever need to make. but they all work on just large-scale quantum interference across this thing. So making the switch is critical. We need it because so much of what we do is probabilistic. And at some point, we realized that the switches that the world already makes, so there's a lot of optical switches in the world already. Every time you're talking on the internet, on your phone, everything that all this stuff that's going down optical fiber is being rerouted by optical switches. And you might hope that we could just take some of the off-the-shelf optical switches that are used in the telecoms industry and use them. And the problem is they're just too lossy. And one of the reasons, and they're too lossy and they require too much power. And we're going to put these things potentially, into cryostats and things. We didn't want to use high power. We didn't want them to be high loss. The way to make them lower loss is to make them shorter. The industry uses this thing called lithium niobate. And so you put a big voltage across, a sort of crystal of this lithium niobate material, and you can make a phase shifter, and the phase shifter becomes your switch. But really, none of this is really good enough. It's just not high enough performance. And so if you look at the material, so what this thing here is essentially telling you is like when you put a voltage across a piece of this material, how much of a phase shift are you going to get? Right? And so what you want is this number to be higher. And lithium niobate is actually not particularly good. It is an electro-optical material, but it's not a particularly good one. And so we invest a large amount of time in this material called barium titanate, which does have a large electro-optical coefficient, but no one was making it in a sort of thin film that we could then manufacture. So where did all the money go? It went into machines like this. This is the world's largest molecular beam epitaxy machine. We have several of these jiggers now. And it just grows. Its sole job is to grow like very uniform sheets of this material, barium titanate, that we can then send to global foundries who can then add it into the layer of stuff we're making on a wafer. And so these machines, one thing I learned is that the operators of these machines are like chefs. The machine is kind of like an oven, but actually making really good materials and doing good material science, it's not a sort of plug it in and play type thing. It's really about having Michelin star chefs that grow the materials for you. And they've managed to do that. They've produced really beautiful BTO. The flatness of the stuff is such that if I blew this pizza-sized wafer up to the size of the continental US, the variation is on the order of a millimeter across this whole thing. It's extremely uniform. Beautiful Pockels coefficients, the highest ones that have been recorded, extremely low loss and so on. And so it took us huge amounts of time, years, tens, hundreds of millions of dollars to make these switches. And now we have them. And now the question is, for me as the architect, how big a switch do we need? What are the performance? Where do we put it? What are we switching where? All of that stuff changes the stuff we make. Oh, sorry. That's the example of a switch. This is just an 8-port switch. Here's the sort of voltage drivers, and this is just showing mapping one port to the other, this kind of stuff. Okay, so switches, enough about the components. The packages, I guess, are the thing where you've broken the wafer up, you're connecting optical fibers, you're connecting electronic circuits and so on. To those chips, that's what they look like on the wafer. Sorry, and the packages are the things we. Oh, what's going on? Sorry. Yeah, things with sort of optical fibers and electronics connected. They're the things to test them. We do somewhat I think of as kind of like silly experiments, but it's really just to test these packages. So we do things like make qubits, send them down optical fibers, do some teleportations. These are things that are not really useful for machine we're doing, but they're useful to convince people that we know how to do a Bell measurement or make the qubits and so on. But really what they do is they test the packages of chips. We need some way of testing a device that's on the order of 5 to 10 chips. So you might as well do some kind of quantum experiment, send it off to nature, and they'll go, yeah, thank you. And that's what happened. So we did some stuff over a few labs here. We got qubits with some nice fidelities and so on. But really, it's not the point of what we're doing, and we now can do much better than these things. Okay. So as you can tell, I'm not particularly excited by that stuff. What I'm super excited about is cryogenic cabinets. And if you'd have told me 25 years ago when I was at U of T that one day you're going to come back and be excited about cryogenic cabinets. I would have thought you were mad. But really, it's something which is important to us, is that to make this very big machine, we have to be able to cool thousands, hundreds of thousands of these chips. And what that means is we need to have cryostats that have a very large amount of cooling. And so do that, we need a cryoplant with liquid helium. And so for a long time, we were kind of rate limited by this to some extent in designing it. But then this is Stanford Linear Accelerator, and they have a cryoplant, and it's like 18 kilowatt cryoplant. And they said, oh, yeah, we're not really using this because we're a government institution. And actually, two of them, one was even turned off. And so they gave us a corner of it to assemble a cryostat and build a bunch of stuff. And so this is how we tested. This is how we can test sort of 1, 2, 3 cryostats and get them working properly. You can see the people assembling chips and putting them in. But the reason I'm excited about it is not because of doing those experiments so much as this guy here. This is the guy making them for us. He's one worker at this company. But the reason why it's important to us is that what this company does is they make Coke machines and refrigerated trucks. Okay, if you go and buy a cryostat from a bespoke, small company that makes dilution refrigerators, and you can't buy 1,000 of them. You certainly can't get the kind of repeatable scale of things that you need. And so we managed to find a company that's used to building thousands of Coke machines and so on. And so they build this stuff for us now, and it's very exciting because it's all working particularly well. So essentially, yeah, that's what gets us to the part of the story. So I've shown you a little bit of everything that goes on here, but the final part is that we need to build the big machine somewhere, and the two places we're doing that are in Brisbane. In this annoying photo, they photoshopped out my lightsaber, but we basically got a site near Brisbane Airport. Here it is, where we're going to build our first, what we call Gen 1 machine. And, I'm going out. This is what it looks like today, empty piece of land. I'm going there on Sunday. Apparently, we started building our first cryo plant there. We also have in Chicago, south side of Chicago, a site. That was the old US Steel Works, was historically a very important site. Now it's empty land. And the Illinois government is basically building a quantum park there, and we're going to be the main tenants of it. And so this, again, is an artist rendering, but we'll have these big warehouse-sized things that will just be doing photonic quantum computing. Last week, I went out there. This is, myself and some of my co-founders. This is the governor of Illinois. This is some fake sand because the ground is too hard to actually dig in with a shovel. And then we were doing this groundbreaking. And I think the important thing to realize about this photo is that none of these people are actually the people who are building the quantum computer. It's all the people I showed you at the beginning, the actual engineers and architects and so on. People like me, we wear a suit, we go shake hands with the governor, but it's these people that really matter for what we're doing. And I think they're doing incredible stuff. And I'm very proud of them and the progress we've made. And yeah, it's expensive, and on an academic scale, it seems insane. But hopefully you have some appreciation and don't think it's quite as crazy as maybe you did at the start. Thank you.
Okay, thanks very much. How are you on time?
Yeah, sorry.
That's okay.
Yeah.
Okay, so we have time for some questions, if there are any. Yeah.
I want to see you guys all running upstairs when you're retired like John.
So thank you for that great talk. So my question is about just the strategy that your company would take. How much committed are you to your initial blueprint and design? So, for example, I see that you've taken some approach to make your resource state generator modules by multiplexing some probabilistic sources. Yeah. Why don't you just now, for example, now that deterministic sources are more available or are...
Yeah, we will, but they're just not good enough yet. But we will. I mean, we have programs on that, but they're just not good enough.
Okay, like you're just waiting for the technology.
Sorry? The purity is just not high enough. So, when you're doing fault tolerance, the size of the machine is sort of decreases exponentially with the better you make the stuff. And so, you know, you really care about even small changes in noise. Like photons that are 99% pure are not nearly as good as ones that are 99.5 or 99.8% pure, and so on. And so, yeah, we're not against it, and we obviously would rather do that. It would make a much smaller machine. But right now, most of that stuff is just science experiments, physics research. It's not engineering challenge yet.
Yes. Thank you.
Other questions? Oh. Get through here.
Thank you for very polished talk. I have two questions. The first question is the efficiency to get two or even more indistinguishable single photons. And the next question is, if you want to implement enough amount of gates, as you mentioned in the earlier part of your talk, how large your platform have to be.
How does, sorry, the very last thing you said?
How large is your platform have to be?
Yeah, okay, so, well, the machine, I mean, I showed you the scale, and that, you know, hundreds of chips per cryostat, or thousands eventually. That gives you a sense of how big the whole thing is. Sorry, what was the first question? The efficiency. Yeah, so we can pump the sources up to between 15 and 20% single photon efficiency, but we start getting multi-photon effects that cause Pauli errors later in the scheme. And so we tend to actually turn the pump power down somewhere between, I mean, it's actually an optimization parameter in the architecture. The simulation tells us this is the best pump power to use, but it typically comes out between 5 and 10% probability of every source making a photon. And then you have to do all the switching and so on. I should say that we never have to create deterministic single photons. Like the error correction that we use is designed to be good at dealing with erasure, with heralded loss. And so if we know that we haven't made a photon, that's fine, as long as we know we haven't made it. And so, and even the loss rates that we can tolerate, you know, sort of the, well, I'm not sure if I'm allowed to say the numbers, but it's like well over 10% per photon in the world line of this thing, right? That we can tolerate. So the reason why we can get away with sort of this, it's kind of a donkey way of making stuff, is essentially just that error correcting codes for erasure are particularly good, and we can leverage those.
Sorry for interrupting. But then how did you get two photon visibility, although these two are not indistinguishable?
Sorry, how did we get one?
How did you get two photon visibility? You showed a kind of, Hongman dip.
Showed the Hong dip? I think they're just delaying a photon.
Yeah. Okay. Sorry.
Yeah.
Thanks for the very interesting presentation. So earlier you mentioned that still today's quantum computers are far from application. So are there any what are the first problems the quantum computers can solve in your opinion, or does the company have any specific ideas of what kind of problems they will tackle first?
Yeah, so we have a whole team. I didn't show them or their work. It's about 40 people, and their sole job is working that problem. They're just algorithms people. They don't care too much about the photonics. It turns out there is some stuff because we have some non-locality in the system that we can leverage, but to zeroth order, they're just doing regular quantum algorithms. And what they do, well, part of what they do is they go talk to potential end users, a pharma company, a car company, or whatever. They do some joint project together, and they try and work out what is the best algorithm, how big a machine would we need in order to make this thing work. And then, they come back with some numbers. And as time goes on, like that plot I showed you, the numbers hopefully come down. The business model for PsiQuantum is not to sell time on the machine to those people. It's to do joint scientific development with them. Why we're quantum physicists, why would we let other people extract the value from the machine?
Okay, thank you.
I should say we're quantum physicists. We think we're smarter than business people. I think we probably are. So why would we let those dummies extract the value from the machine?
Any other questions? No? If not, then let me ask you to join me in thanking Terry again for a great talk.